Jnanam paramam dheyam. Knowledge is supreme.
Let us now see how a first order system reacts to a disturbance. So, we will look at two most commonly used disturbances. One is a step disturbance and other is a sinusoidal disturbance, and we will try to see what are the responses of first order system when there is a first order lag or a purely capacitive system, and then we will try to see the significance of the two parameters Kp and tau. So, the first type of disturbance we will analyze is a step disturbance or step input. So, we have a transfer function for our system which is a ratio of Laplace transform of output to the Laplace transform of input, which for a first order lag is Kp over tau s plus 1. We will look at unit step response. So, the Laplace of that would be A over s, where A is the step size. So, if we want Ys, it will be Kp over tau s plus 1 times Us, which is Kp over tau s plus 1 into A over s. So, that gives, so Ys is equal to A Kp over tau s plus 1. Now, in order to get the response in a real time domain, we will have to invert this Laplace, and the method we are going to use is method of partial fractions. So, what does that mean? We will split this transfer function or this Laplace transform into parts for which we know the inverse. So, in this case we can write Ys is equal to A Kp, and the denominator has s and tau s plus 1. So, if we add two fractions like this and take two coefficients as small a and small b, then the addition of these can give rise to this 1 over s tau s plus 1. So, the idea is we have to find these coefficients a and b, and then once we have that, we know the inverse Laplace of 1 over s. So, Laplace inverse of 1 over s will be a constant or a unit step, and the Laplace inverse of 1 over s plus a is e raised to minus a t. So, once we have converted it into a partial fraction, we will be able to get the inverse of the final output. So, let us try to find out how we get these small a and b. Which has to be equal to A Kp 1 over s tau s plus 1. So, we can write A times tau s plus 1 plus b has to be equal to 1 for all values of s. So, in order to get any coefficient, we can simply substitute appropriate value of s. Let us put s equal to minus 1 over tau . So, we will get minus b over tau equal to 1, which gives me b equal to minus tau. We can substitute s equal to 0. In that case, we will get a equal to 1. So, what we have is Ys is equal to A Kp 1 over s minus tau over tau s plus 1, which we can again rearrange. So, we have represented Ys as sum of the two fractions for which we know the Laplace inverse. So, if we take inverse Laplace now, we will get Yt will be equal to AKP. This inverse of this will be a constant, which is 1, minus the Laplace inverse of 1 over s plus a is e raised to minus at. So, it will be e raised to minus t over tau. So, that is the response of a first order system to a step change of the size a. So, let us now try to analyze how does this solution look like and what is the importance of these two parameters Kp and tau. So, if we plot the response of Yt versus time, the plot we are going to get so at time t equal to 0, when we substitute t equal to 0 in the response, so let me just rewrite the response here as well. Yt is equal to AKP 1 minus e raised to minus t over tau. So, when t is equal to 0, we have e raised to minus t will be 1. So, we will have 1 minus 1. So, that is 0. So, the response will start at the origin. Now, let us consider what is the final value of this response. So, let us consider t tending to infinity. As t tends to infinity, e raised to minus t will go to 0. So, the final value of the response will be AKP. So, if this represents AKP, so for a very long time the response would somehow reach this or approach this particular line. Now, let us look at how does the response change as a function of time. So, we will calculate the derivative of the response, which we can get as AKP over tau e raised to minus t over tau. So, if we look at the derivative at time t equal to 0, it will be AKP over tau, which is greater than 0. So, our response will have a positive slope at time t equal to 0. So, the response is going to kick off at time t equal to 0, and if we simulate or plot the actual values of this function, the response would look like this. So, this is the response of a first order system to a unit step change. So, we can now look at what is the total change in output is the change from start value to the end value, that is AKP minus 0 is equal to AKP, and this change in the output was caused by a change in input of the value A. So, if we look at what is the magnification of the effect of u, we can find out delta y over delta u, that is a total change in output to a total change in input, that will be AKP over A, which is equal to Kp. So, Kp represents how much the effect of input gets magnified when we will see that effect in the output, and it sort of acts as a gain between input and output. That is why it is known as a process gain. So, it tells me if the input changes by 5%, then the output will change by 5% times Kp. So, that is the significance of one of the parameters of first order system, which is the process gain. Let us now try to see the response as a function of time and try to capture how the response changes. So, we will make a chart of time and the corresponding value. So, at time t equal to 0, the output was 0. Now, if t was equal to tau, so if we go back to the previous slide, if we take time equal to tau and find out the response, that response will come out to be 0.632 times AKP. So, when time is equal to tau, the response we get is 0.632 times AKP, which is same as 63.2% of the final value, as the final value is Kp. So, within the interval of time t equal to tau, we have already completed the journey up to 63% of the final response. If we look at the similar value at 2 tau, the value we are going to get is 0.865 AKP. So, within 2 tau, the system reaches almost more than 85% of the final response. In 3 tau, the similar value will come out to be 0.95 AKP. And lastly, if we calculate up to 5 tau, it will come out to be 0.993 AKP. So, that is 1% of the final value, within 1% of the final value. So, for all practical purposes, that is almost equivalent to considering the final value. So, we do not need to consider the response up to infinite time. We typically would consider the response up to t equal to 5 tau, which sort of tells you that the system has reached the final value. So, if we want, so what does that mean is the speed of response of a first order system is directly tied to this time constant tau. If the tau is small, then correspondingly 5 tau will also be small, and then we will have the system will reach its final value at a faster rate compared to a system which has higher tau. So, speed of response is related to tau. Smaller the tau, faster will be the system. So, that is the significance of time constant. If we are comparing two first order systems, then we can compare the speed of response by comparing the values of tau for the two systems. Now, before moving forward, let us also see how a purely capacitive system or an integrator reacts to a unit step change. We have the process transfer function g of s is equal to Kp over s. We will take us as a over s. So, we have ys is equal to gs times us, which gives us a Kp over s square. Now, Laplace inverse of 1 over s square is t. So, the response we are going to get here is AKP t. So, the response linearly increases as a function of time, and the slope of the response will be AKP. So, in this case Kp somehow tells me about the speed of response. Larger the value of Kp, larger will be the slope, and the faster will be the system reaching its ultimate value, which in this case is the physical limitation on how much the output can change. Mathematically it will go to infinity, but physically there will always be some limitation or maximum value of y which it can take. So, it will, maybe if it is a tank, it is the 100% level of that tank. So, the higher the value of Kp, faster will be the system response to go to the final or the extreme limit. Thank you.